Welcome to Scene from Above, Season 15, Episode 4. In this episode, Julia Wagemann speaks with Aimee Barciauskas, a data engineer at Development Seed. For 7 years, she has been working with NASA's Impact team, helping the agency on its cloud migration journey and making vast volumes of Earth observation data truly cloud-friendly. Through projects like the Multi-Mission Algorithm and Analysis Platform, she's been instrumental in building the ecosystem of tools, metadata, and community documentation that makes working with petabytes of geospatial data accessible and intuitive. In this episode, we learn more from her about what cloud-friendly really means, the technical and cultural barriers we still need to overcome, and how frictionless reproducibility might shape the future of Earth science.
Aimee, hi, welcome to the Scene from the Above podcast.
Hi, thank you so much for having me.
So, Aimee, you are a data engineer at Development Seed, and you work also on many NASA projects where your role is to make large volumes of Earth observation data cloud-friendly. In your own words, what does cloud-friendly mean with regards to Earth observation data?
Yeah, so just a little bit of more background about me and my role here at Development Seeds. We are a organization that focuses on open source software development and partnering with other organizations to basically help them solve really hard challenges with geospatial data. So I've been with Development Seed for 7 years, and during that time, I've mostly been fortunate enough to work with NASA and a really great team at NASA called Impact. And with that team at Impact, we're really trying to help NASA on its sort of cloud migration journey. So NASA's already made a lot of progress to move most of its collections to what it calls its Earth Data Cloud. And so it already has many petabytes of data on Earth Data Cloud. What we want to do is, now that that data is there, we want to make it more cloud friendly. So what does cloud friendly mean, right? First of all, I'm going to sort of harken back to something that Jed said, which is that cloud isn't just, often it connotes like the commercial cloud. But when we're talking about cloud, we don't want to just think about the commercial cloud, because that can be a little bit like of a misdirection. What we really care about is optimizing for working on a network, right? So it's not just about the cloud, it's about using the internet in general to basically provide greater access to people to data and resources. Because, what a lot of people who've worked with geospatial data have found is it's big. You need a lot of compute, you need a lot of storage. So I really like to think more of it as like, what is, network friendly. So that's the first part, is like, basically when we think about cloud friendly, we're more thinking about how do we optimize this data so that people can access it over a network. And then the second part of this is friendly, right? And to me, friendly just means like not intimidating and intuitive. So that sounds relatively straightforward, but it's actually really not. When you think about these massive heterogeneous data sets, it really means building like a whole ecosystem so that what the end user sees is just a simple API into data, or a simple visualization and a simple interface into that visualization. To me, when I say cloud friendly, it really means building an ecosystem where everything that the user is trying to do with geospatial is like easy and intuitive. So breaking that down, yes, first we have to move data to the cloud. But like, just to pause here for a second, like, that is specifically not in itself cloud friendly. If you just put a bunch of data on the cloud, it's not necessarily going to make that data very friendly. But that's really just the starting point. And then what we need to do is build metadata and indexes into that data so that it makes it easy to find. And then we need libraries that know how to read that metadata and those indexes so that people can easily find just the data that they need, right? Because they don't want to be downloading whole files or whole collections of files. And then finally, we need like a community, right? So we need documentation, we need outreach. And this to me is like this whole community that we're working on right now with, the Cloud Native Geospatial Foundation or Forum, I should say, and the Pangeo community and other communities, hopefully I'll talk more about later on. But yeah, that's what cloud friendly means to me, is like building that whole ecosystem and then making it accessible to everybody through a broad system of like tools and documentation.
So collaboratively working on making the cloud work for Earth observation data. So yeah, this is how it is a challenge. And tell us your story. How did you start working with geospatial data in the cloud?
Yeah, well, it's definitely all reference back to also what Brianna said. My path was also very nonlinear. So I started out studying economics. I really wanted to be a development economist. So I wanted to do something with data. I love the fact that data could tell stories and explain, like physical phenomena and social phenomena, and using data as a tool to basically inform, policy making and actions like on the ground. So that's what I've always been passionate about, I would say. And when I graduated with an economics degree, I didn't exactly find that type of role that I was looking for. What I found was like really to be sort of an economic researcher. You really needed a PhD, which I wasn't prepared to go for. So basically, in my first job, I wasn't really passionate about, and I started doing sort of software development, I would say, like on the side. I took some courses and basically was able to take that experience or that education, and it led me into eventually a full-time job in software development, which was awesome, and I loved it, and it felt extremely like empowering to be able to build websites and build APIs. And then that's when data science became a thing. So data science became a thing, and I realized like, oh, this is the perfect marriage of my two passions of programming and statistics. So I took a year to basically get a master's in data science. I was very fortunate enough to be able to do this in Barcelona at a school called the Barcelona Graduate School of Economics. And when I graduated, I did realize I don't want to be a data scientist. It's really an awesome profession, but there's a lot of sort of business decisions involved in being a data scientist, and I really wanted to do more of the groundwork in like data engineering. So that's kind of what led me to my first job after that, which was in an awesome company called Nava, where we built websites for basically people to access social services like Centers for Medicare and Medicaid, and they also worked on healthcare.gov. And then from there, I found Development Seed. Both these companies were located in DC, and I was very excited to learn about Development Seed and its mission. And so that brings us to today, or like 7 years later from when I started at Development Seed. When I started Development Seed, I really had no knowledge of geospatial data, earth sciences, all those domains. And I was able to sort of jump into this world because of my passion for like programming and cloud computing. And so that's been a really great opportunity to get involved in this space and really address my passions of like wanting to solve humanitarian challenges like climate change with technology.
Oh wow! So you're like a self-taught software developer. So it's like super impressive. And then you at Development Seed, so like you brought all your knowledge you collected from diverse backgrounds, like from economics and data scientists and software developments, which are really important skills. But then you first got introduced to earth science applications, I imagine, and
Mm-hmm.
earth observation data. So how was it for you to get started with geospatial data and satellite data?
Yeah, I would say that it was a lot of just being curious. And with my projects, fortunately, I was fortunate enough to start at Development Seed working on a project called the Multi-Mission Algorithm and Analysis Platform. It's a cloud hosted environment where scientists can get together, and specifically the type of scientists, what the science that they were doing was to study above ground biomass, which is kind of a fancy science term for measuring the total mass of like trees and all of these other plant life. Like the reason why they would do this, right, is to sort of measure things like the impact of deforestation on this important carbon stock. Yeah, so just there, like I wouldn't, before I started Development Seed, like I would not have been able to like describe that in those terms, right? And just by being on that project and being exposed to the science that was being done there, like I sort of learned that way, just trying to understand what the scientists were trying to do on this platform. And that's continued through today, through this evolution of MAP to this new platform called the Visualization, Exploration, and Data Analysis Platform, or VEDA, at NASA, which is really trying to generalize some of the things that were really successful about MAP, as well as a dashboard that we built for COVID-19 into a reusable platform for different earth science domains. So definitely through my project work was one way that I got to learn about earth science. But I would say another way for anybody else who's interested, not working at Development Seed or with NASA, definitely conferences are a great way to start to learn more about earth science and geospatial technologies. And then the community, right? So I think community is really important. I think without community, people won't necessarily stick with a thing. You can listen to a podcast or you can do a tutorial, but you won't necessarily stick with it unless you have that community around you. So I was really fortunate to be able to get involved in some of these communities through Development Seed. So just to name a few, Pangeo, which I already mentioned, Earth Science Information Partners is another really great one. And then I would say there's a lot of great developer communities out there as well. So if there's a particular library that you're interested in, you should definitely just, reach out to the core developers of that library and say hey, do you guys have a community meeting or suggestions where I could learn more?
No, thank you for all these helpful recommendations. I think in the Earth observation field, there's also a few who are in a similar position than you were 7 years ago, joining from a different background and then needing to learn all things about Earth observation and geospatial. Would you say, or can you point it down, what were the biggest challenges you had when you started working with Earth observation data and technologies?
Definitely the data formats, which I'll probably talk about more, but just trying to understand the data formats themselves and how to read them with the variety of libraries that are out there to read them was a challenge. I'll give you one example. When I remember earlier on when I tried to create an image of a geotiff, and I can't even describe the wonky things of random lines and just black boxes that showed up and, not knowing what I was doing wrong. So definitely just trying to understand those data formats and the libraries to read them was a big challenge.
Yeah, I can imagine. But now basically you mastered it because you are the author of a very popular online book on cloud optimized data formats. And I think you now give guidance to many to help uptake the cloud native geospatial data formats. So well done.
Yeah. And I'll just say too, for my part, I know a lot of people are like this, but I'm definitely more of a doer than, a structured learner. I love to try things out and, break things. So I definitely learned through a lot of trial and error. And I definitely think if other people, if that's the way you learn, you should just pick up a project and just keep hammering away at it until you figure it out.
Yeah, more room for failure, right? Because through failure, you learn and you can improve. So maybe from your perspective, because you've been in data science, which is just a broader term of all things in geospatial quite from the beginning. How do you see the skills changed throughout the past 10 years? And do you see also a specific skill set appearing that specifically Earth observation, geospatial practitioners might need because we see the shift to cloud and geo AI, for example?
Yeah, so definitely I feel it's an interesting time to be asking this question. I'll start with I would definitely say today, especially true a few years ago, but definitely today as well. I think I share a vision with a lot of people in this community that within earth science and analysis, we're moving towards a more openly collaborative, collaborative through code specifically type of future. So this is why I'm really excited to see that a lot of earth scientists are learning programming. And so I think basic skills that you need to learn to be a part of this sort of like, sort of rapid progression in earth science advancement would be, learning coding, specifically Python. A lot of the modern geospatial libraries are in Python. And then Git and GitHub. And the reason why Git and GitHub are so important is because if you want to sort of learn from other people what other people are doing, you can, go and check out their code and you can try and iterate on it. Further, you can also put your code that you're working on Git and GitHub, and you can get feedback on it. And I think that sort of like iterative loop of trying something somebody else built and then putting your attempt online and sort of iterating through Git and GitHub is really powerful. So definitely those skills are the foundational ones. But I do think it's an interesting time to be asking this question as well, because a new skill is just understanding what you can do with AI. And especially as a developer, of course, like we can go a lot faster just by using a lot of the sort of, and using, at least using them well, learning how to use them. A lot of the tools that are being developed, like ChatGPT and Perplexity, et cetera. That being said, it's also interesting because those tools themselves are actually going to make geospatial data more accessible in the long run, right? Like it's going to make it really easy for you to just, hopefully like ask a question. But yeah, I definitely think if you want to participate in actually like earth science and data analysis, I would definitely start with Python and Git and GitHub.
Do you already experiment using ChatGPT or other AI tools for code creation and in your day-to-day work?
Yeah, I do. I think it's really powerful. I think we all have to be very cautious and thoughtful about how we're using these tools. We have a really great team here at Development Seed. One of my colleagues, Danny, like he also is always like informing us about the latest and greatest tools. What I would say is my personal approach or philosophy is it's really good to try everything and see what it's good at. Well, I shouldn't say everything, but it's really hard to try everything. There's so many tools out there, but to try everything that people recommend and to figure out what they're good and good at. But then when you're actually trying to use things for a task, I think it's important to be thoughtful for two reasons. One is that, it's this sort of typical problem of when you have a hammer, everything looks like a nail. Like you don't want to just use these things arbitrarily for random, for different tasks that potentially you could solve yourself. And I guess that leads me to my second point, which is that you don't want your skills and understanding to atrophy by being overly dependent on these tools, right? So I think it's important to use these tools because they can make you go faster, but not because they can like make you dumber. Basically, like you want to keep learning yourself, but you want to understand what the model is doing and why it's doing it, and you want to thoroughly like, understand what it's produced. And to do that, you can't just like be along for the ride. You have to be an active participant.
Thanks for phrasing it so nicely, because there's this risk that you lose that skill to actually think about a problem, because you always get a solution and it's always just easy to take something.
Yeah, exactly.
Instead of really starting without something and from scratch or with a blank paper. It's often also good to also just with writing to sort your thoughts and then maybe getting some ideas additionally. Yeah, no, thanks for sharing. You're the main author of the Cloud Optimized Geospatial Data Formats Guide. And this is like now one of the upskilling areas in Earth observation, I would say, moving to the cloud. Do you have specific recommendations to people on how they can get ready for cloud-based workflows and start out with geospatial cloud computing?
My favorite resource for this at the moment, I mean, obviously the Cloud Native Geospatial Guide is a great resource if you want to just learn about the different formats that are available. But actually, my favorite resource for this type of thing is I've been fortunate to be a participant in the University of Washington's eScience Hack Weeks, which are focused on different earth science disciplines and also like NASA missions, like the ISAT-2 mission. These sets of tutorials that they have are all completely online. They're a really great resource for getting started with cloud computing and also getting started with all of these geospatial data formats. So yeah, I would definitely recommend looking there. Project Pythia is also a really great resource for learning more about cloud computing and an introduction to geospatial formats and some of the tools to use.
One of the goals of the series is also to demystify the term cloud native geospatial. You probably also heard from previous guests, we always ask, in your own words, what is cloud native geospatial?
Yeah. So first of all, I like to think about what we did before we had the cloud, right? And I wasn't, I wasn't a part of this, but we have all of these geospatial data formats, and essentially they were not designed for the cloud. They were not designed for network-based access. They were designed for you to work with them mostly on your local machine. So from a starting point, I think when I think about cloud native geospatial, I think about the fact that these files were not designed to be used on the cloud. And so what does it mean for us to make an ecosystem where now this data is accessible from the cloud? So that means basically, restructuring and reorganizing the data itself. We are living in a world where now all these files are available online, but without the right, like I said before, like without the right ecosystem and structures in place, it's still going to be just as hard to work with them. So to give a specific example, a lot of these files, these archival file formats like netcdf, hdf, geotiff, grib, to give some examples, they have all their data organized in really small pieces and all the metadata scattered. And the reason why this matters is because when you have a network introduced, every request introduces latency and overhead. And so you don't want to make tons of requests for your data. You want to sort of get just the right amount of data with each request. So this is actually, it sounds simple, but it's pretty complex. And to explain why, I like to use this analogy of grocery shopping. So if, most people have to go grocery shopping, and you go to your local grocery store to do that. And when you go to your local grocery store, you know where everything is, and you can just easily pick up like individual items. And that's kind of like reading data on your local machine, right? It's fast. It doesn't really incur a lot of like overhead for you to like think about where things are or how things are packaged. But now we have Amazon.com. Like a lot of people are like, oh, I can do my grocery shopping on Amazon.com and I can do so much more. And that's kind of like the cloud, right? Because it's like with the cloud, we can do so much more. If you think about Amazon.com's fulfillment centers, they look absolutely nothing like a grocery store, right? They put all of these items in bins and they have conveyor belts and they have a very complex system for basically how you ship things to people. And so this is a good analogy for me for thinking about like why the ecosystem has to be so much different, because we need to think again about, how we package things efficiently, how we put things close to each other that might be requested together, and then also how we route those things, right? Like Amazon has these really efficient like delivery routes as well. So all of that comes into play. That's just particular to like any cloud architecture. Making this like geospatial specific, we are thinking about how to organize data in a way that people like make sense for the way people will be requesting it. So we put things together that have similar types of geospatial queries, right? And that's usually like spatial and temporal. So yeah, to summarize, like cloud native geospatial to me basically means rethinking this whole system so that it makes the delivery of geospatial assets to people in the most efficient way, given like how they might be asking for them.
I liked it analogy a lot. Probably next time when I go grocery shopping, I think of a traditional file system.
Yeah.
No, thanks so much. So regarding the cloud native geospatial and all the developments that are currently ongoing and will also be even more so in the future, how do you see your role in shaping it?
Yeah, so I see my role fall into basically two modes, which is the first one I've mentioned already, which is basically my role in NASA and this relatively new platform called Veda, again, which stands for the Visualization, Exploration, and Data Analysis Platform. This platform is a concept that we came up with to basically demonstrate the concepts of cloud optimized data and cloud native data delivery. And my team within Veda is called the Optimized Data Delivery Team. So we're basically in charge of trying to figure out the most optimal ways to deliver data. And that means both for analysis and for visualization. So definitely progressing like those technologies within NASA and within Veda platform itself is one role that I have. The other one is my community roles. So I've already mentioned Pangeo a number of times. I'm a member of the Pangeo Steering Council and just, sort of general advocate for it as a community. It's a really welcoming place for people to get started with geospatial libraries. A really core value of Development Seed and Pangeo is open source software. And that's really important to this community aspect in general, but those to Pangeo and Development Seed, because basically with open source software, we can really empower people to basically solve their own problems. And so that's why I find like the Pangeo community really exciting, because basically the founders felt that they wanted to basically solve really challenging geospatial problems with open source software. Then the other community that I'm a part of is the ESIP Cloud Earth Science Information Partners. I'm the chair of the Cloud Computing Cluster. So that's another, I would say Earth Science Information Partners in general it has many different clusters that you can join. I just mentioned one, but if you're interested in other domains of earth science, like you can definitely join one of those clusters as well.
Okay. So as a member of these, like Pangeo, or like even more than a member, like a steering committee member of the Pangeo project, and you also said that you're like the chair of the ESIP Cloud Computing Cluster. You said like this is a great way for you to shape the current and the future direction. If you think about the future developments, what are you mostly excited about?
Yeah. I love this question because, who doesn't want to talk about what they're excited about? But I'm most excited about the fact that there's technologies now that enable us to access all of these files as logical data sets. So stepping back, what is the problem we're trying to solve? So like I mentioned, we're putting all of these file formats, all these different files on the cloud, but that does not necessarily make them very accessible, right? And there's new file formats, which you call like cloud optimized file formats. And some of these would be like cloud optimized GeoTIFF, ZAR, and GeoParquet. And that enables us to access just pieces of the data. That's why we call them cloud optimized, is you don't have to download the whole file, right? You can just access the specific pieces that you want. Now, what we can do is, because the challenge is that these data providers, right, they don't have the time or resources to necessarily create and maintain copies of the data. And I don't think that they actually should have to, right? That's a huge additional burden on them to create a cloud optimized version of the same data that they've already, created and worked on. So what's come about in the past couple of years is a concept called virtual ZAR. So just very briefly, what is ZAR? ZAR is a specification for multidimensional data. So if you think generally about, geospatial data and the way that it can be stored, doesn't matter the data format. It's almost always these long arrays of data with metadata associated with it, so you know how to read it. So regardless of the data format, that's like the basic structure of the data. And there's all these different data formats, like I mentioned previously, but they're all doing a similar thing of storing these arrays of data and then storing metadata that enables libraries to read that data. So with the new technology, we can basically access these archival file formats like a single logical data cube. And we can do that through this ZAR specification. So the ZAR specification basically says, hey, here's some ZAR metadata about these arrays. Here's a mapping of all of the data across these files. Now we can access all of these files as one massive, logical data cube. So the libraries that have made this possible our Chunk, a library called virtualizr, and now we also have a library called IceChunk, which enables us to store that ZAR metadata and those ZAR manifests in object storage. So yeah, I'm really excited about this, is basically making like many, many multidimensional data sets like more accessible.
So the virtual SAR is library that allows you to access many SAR files.
It's a little bit confusing because of the terms, so I'm just going to restate it again. Like virtual ZAR is a concept, right? Where we're basically creating ZAR data sets, but they're virtual in the sense that the data itself doesn't need to be stored in the ZAR data format. It's virtual because we are just constructing ZAR metadata that enables us to access that all of those underlying file formats, which could be a wide variety of file formats, it doesn't matter, as a ZAR data set. We have a library that helps us basically create all of that metadata.
Okay, great. Thanks for reiterating.
Like the concept in the library. So they're similar names, but yeah, just to differentiate.
Would you say you are more excited about SAR than about other cloud native formats?
No, I definitely wouldn't say that. I would say that I'm most familiar with ZAR because, and I mean, might be most excited about it because there's a lot of really popular large scale gridded data sets that can fit into this model. But I do definitely think that other cloud native formats that have come about for other different types of data, so GeoParquet for vector data, cloud optimized point clouds or COPC for point data, and cloud optimized geotiffs are also going to play an important role in this whole ecosystem.
So you wouldn't say that SAR will replace cloud optimized geotiffs?
No, another thing that my team is excited about is we're working on basically creating virtual ZAR for cloud optimized geotiffs, right? So enabling a ZAR interface for those cloud optimized geotiffs. And that could be that will be really cool and powerful to basically treat a whole bunch of cloud optimized geotiffs like one logical data set. But just to be clear, I also think that like cloud optimized geotiffs as a format and what they do well is when you have like spatially disaggregated data. So one constraint that we sort of have with ZAR is that all the data within one array needs to have consistent dimensions, which basically just means like, hey, they need to have all the same like latitude, longitude coordinates and all the same temporal time steps. With cloud optimized geotiffs, one of the things that they do really well is the fact that you can have data sets that are very disparate, right? They're disparate in time, disparate in space. And so that's still a really good way to store that type of data.
So what barriers and limitations do you still see that we need to overcome as a community and also as an industry?
Yeah. So I think there's like three main categories of challenges. The first would be technical. The second would be operational, and the third would be cultural. So I'm just going to talk briefly about each one. So technically, the challenges that we face are we still live in a pretty complex network environment, right? So we have these different cloud providers, and data is still dispersed across these cloud providers. So just solving that multi-cloud challenge is like a technical challenge. For example, there's also there's still a wide variety of data, like I mentioned, right? So creating like a cohesive ecosystem for different types of data. So say, with Earth observation data, for example, we have these large gridded data sets, but we also have point clouds, and we also have, lower levels of data, like less processed into a grid. So how do we treat all these different, data products in one like cohesive ecosystem? But technical challenges are actually, I think, for this community, like the easiest ones to solve. Like, I think all these things are solvable. And I also think that there's tools already in place, like I've talked about, to solve the big multidimensional data set challenge. So I think that we, just because there's a lot of challenges out there doesn't mean we shouldn't also do like the easy stuff as soon as possible. On the operational side, I think, one of the big challenges that we face there is that these large data providers, like I sort of mentioned this before, but they already have a lot of obligations to deliver these data products, and they have a lot of users that depend on these data products and the associated services of those data products. So it's challenging to ask them to adopt a new technology in the face of that, right? They're constrained with both finances and resources to implement them. And I don't see that changing anytime soon, especially like in our current context. So that being said, it's a challenge that we need to face because we are actually, we're asking them to adopt some of these pretty new technologies. And the reason why we're doing that is because we believe that they can be transformative, right? We believe that they're going to be able to sort of unlock these archives of data sets to many more people and many more use cases. And we also are advocating for them because we believe that we won't harden these technologies without testing them out in production. And it's a little bit of a paradox because, they have a hard time picking up these technologies without them being proven, but we can't prove them without trying them out on real data and on our real users. So we're fortunate that we get to work with a really innovative group at NASA, and NASA as a whole is pretty liberal in its adoption of new technologies, I would say, for such a large organization. So I'm optimistic that we will solve that challenge. The last challenge I just wanted to mention, is this cultural challenge of the fact that, at least within earth science and academia, there still seems to be very much this culture of publish or perish. And the reason why that matters is just because that means a lot of academics are still going to be sort of protecting their data and their workflows and not necessarily prioritizing a sort of cloud first collaborative approach. And so while we can come up with all of these strategies for adopting cloud native and collaborative approaches, I don't think they will make it into that community without changing the culture. And I love this quote by Shel Gentiman that culture eats strategy for breakfast. So yeah, like I said, even if we have all the strategies and we implement it, like if we don't change the culture, I don't know if it will impact that community as much as we want.
Yeah, well said. No, thank you for sharing your perspective and also the three different limits and barriers on three distinct areas. So what is your perspective on, if you look ahead 10 years down the road, how does the future of geospatial in the cloud look like?
I definitely think it is the data itself by necessity will need to be on the cloud. I think the NASA number is like 600 petabytes by 2030, which, is hard to even grasp how much data that is, but it definitely necessitates, some cloud storage. But I think I'm hopeful, and that in the next, hopefully sooner than 10 years, but yeah, 5 to 10 years, that the practice of earth science and geospatial exploration like necessitates this new mode of working. And to describe why I think about like David Donahue, he wrote this article called Data Science at the Singularity, which which is an interesting title, but what he mostly talks about is this concept of frictionless reproducibility. And he talks about it in the context of empirical machine learning. So, we've already talked a little bit about AI, but the fact that AI has progressed, specifically like computer vision and LLMs, one of the reasons why it's progressed so rapidly in such short amount of time is because of this concept of frictionless reproducibility. So, what does that mean? It means basically sharing of data, making workflows reproducible so that people can reuse the data, reuse the workflows, rebuild on existing models to make them better. And the last element is, in machine learning, there's all of these competitions, right? Like these computer vision competitions. So you have these benchmarks that people can benchmark the models against and really advance the field in that way. And I think, earth science practitioners and geospatial data explorers might be looking ahead of them saying, like, why are we being left behind? And I think I'm hoping that like by necessity, like needing to sort of match that rapid progress in insight will sort of motivate people to learn, adopt these new practices of like computing and collaborative development.
I think that's an excellent closure of today's episode. Yeah, Aimee, thank you so much for your time today and sharing your perspective and valuable insights. I think this will be very helpful for many who just start out on their geospatial cloud journey.
Yeah, thank you so much.